I'm Peter James, and this talk is about using gravity anomalies to study the inside of Venus. Venus is called Earth's sister planet because it's similar in many ways, but it's very different in other ways. It's important to investigate these differences in order to better understand why our own planet is the way it is, and to better understand the diversity of Earth-like planets that might exist in our galaxy.
So, no parent is allowed to have a favorite child, but every planetary scientist will have a favorite planet. I see some nods. And if you're not paying attention, then you might not know what mine is. But here's a comparison of Earth and its two neighboring planets. So, which planet is most similar to Earth? I'll ask you. Well, in terms of size, Venus is about the same size as Earth, while Mars only has 1/10 of the mass. Venus is a little bit closer, even though they're sequential in orbits. If you stood on Venus, it would feel like Earth. You have normal gravity. The rock compositions are very similar. A lot of people don't know this, but while the United States was sending astronauts to the moon with the Apollo program, the Soviet Union decided to make Venus their thing. So they sent lots of robotic landers, that some of which made it to the surface and took measurements, and they found basaltic compositions, which is similar to the kind of rock that you find on Earth's oceanic crust, Hawaii, places like that. And basaltic compositions that they found are derived from a peridotite mantle, which is also similar to what we have on Earth. So it looks like, in terms of the rock composition, Venus is made up of a lot of the same stuff as Earth. And then finally, Venus is pretty geologically active. It has volcanoes, rift zones, tectonics that I'll come back to a little bit at the end of the talk. I am underselling Mars a little bit. There are plenty of reasons to be interested in Mars. It has interesting climatic stuff going on. But the point I want to emphasize is that in terms of a planet that fits all the stats of Earth, there is no other planet that we know of like Venus. We've discovered thousands of exoplanets in the past decade. And at least in terms of size and distance from the star, we do not yet know of a planet that is more Earth-like than Venus. So that's really important as we're trying to find Earth 2.0 around another star. Because here's a planet that looks very similar to Earth in a lot of ways, and yet it's a completely different planet. It's 800 degrees on the surface. The longest lived of the Soviet landers that I mentioned lasted just over 2 hours before they died from the heat. Atmospheric pressure is much higher. The atmosphere is 90 times more dense. It rains sulfuric acid. When it comes to water, it's bone dry. The atmosphere rotates faster than the planet itself does, and that's a weird thing that general circulation modelers struggle to explain. And there's no magnetic field, and a lot of these differences might come down to the geology. Venus doesn't have plate tectonics as we are familiar with it. Instead, it has something called a stagnant lid regime, where there's no recycling of the crust that allows some of the volcanic gases to build up in the atmosphere. If you don't have subduction and the heat engine that goes with it, then you don't have as much heat flux coming out of the liquid outer core, and then you don't have a dynamo and you don't have a magnetic field. If you don't have a magnetic field, then the solar wind can come and strip away a lot of the lighter elements in the atmosphere, and you can lose a lot of your water that way. So you have a planet that started very similar to Earth, but due to very small differences that we have yet to fully understand, it took a completely different path. So it's really useful to study Venus in order to understand why Earth is the way it is. For example, scientists first discovered the chemistry of the ozone layer while trying to understand Venus's atmosphere. There's a lot we can learn about this regarding our own planet And then also, as we're looking for Earth-like planets orbiting around other stars. So, Venus is a very interesting planet. That's my pitch. It is crucial for understanding why Earth is the way it is. And so, one of my goals in research was to try to determine if it doesn't have plate tectonics, how do some of the continents form on Venus? And there should be a globe that you guys can pass around, and you can see some of the radar topography from Magellan on there. The redder colors give higher topography, and so you see that there are some structures that look like continents on Venus, along with globe. So how do those continents form? There have been two different broad theories, essentially. One of them involves an upwelling where you have the mantle flowing up. As it rises up, it decompresses and trickles through, finds its way to the surface and thickens the crust. And in the process of doing that, you end up with the melt residuum, where some of the iron and aluminum is preferentially melted, and what you leave behind is less dense. So the result is that you have this hot residuum underneath some of the continents. And then the other idea is basically the opposite, that there's a downwelling, kind of like converging conveyor belts that ram the crust into itself and creates this buildup of thick crust over a downwelling. So we could test these different models if there was a way to peer into Venus's mantle. And we can. To do that, I need to take you back to the 19th century and a man named John Henry Pratt. So Pratt was a chaplain with the British East India Company, and he had a hobby of applying mathematical principles to the Earth. While he was in Calcutta, he was approached by the Surveyor General of the Great Trigonometrical Survey. So this was a really ambitious project to precisely map the entire Indian subcontinent. If you look closely, you see little triangles on here, and those are leveling lines. So they would level out to a point and then level back to make sure to ensure internal consistency. And they would very laboriously map out the entire Indian subcontinent, and then equally laborious was the task of doing all the trigonometry by hand back in the offices. So they were doing this, but they were running into some problems because in the northern part of the country, they couldn't get internal consistency. So eventually there was a guy by the name of George Everest, namesake of the mountain, who figured out the problem that the plumb lines were being deflected toward the Himalayan mountains. And that was messing up their internal consistency. So they went to John Pratt and asked how he could, if there was a way to explain this. And does anyone have an idea what that might be? Why would a plumb line be deflected toward the Himalayan mountains?
Because there's higher gravity there?
Yes. So Pratt said, aha, according to Sir Isaac Newton and his law of gravitation, any sufficiently large mass will attract other masses. So if you have something as large as the Himalayan mountains, then you would expect there to be some amount of gravitational pull, and that would be deflecting the plumb lines. So thus was born the technique of using gravity to determine the distribution of mass in a planet. It wasn't quite that easy. So he did the calculations, and we know the density of the mountains pretty well. We know how much volume they take up. But then the answer he came up with was still a deflection, but much less of a deflection than was observed. So why would that be? Why would you get less of a deflection toward the Himalayas? We know the amount of mass. We know the equations for gravitation. What he eventually realized was that there even though there's an excess of mass in the Himalayas, there must be an accompanying deficit of mass underground. And really that should make sense. This is a theory of isostasy. Isostasy is best illustrated with an iceberg. So, you know, an iceberg is floating in the ocean. There's a little bit of the iceberg that pokes above water, and then a lot of it underwater. So the mass of the iceberg that's sticking out of the water is roughly equal to the upward buoyancy of the portion of the iceberg that's underwater. Or you can also think of it as the mass of the water that's being displaced by this iceberg is equal to the mass of the entire iceberg. When you apply this to Earth, as a first approximation, not exactly, but the amount of mass in any given column of the interior of Earth in a state of isostasy will be roughly equal. If you have a thicker crust with a root, you have more mass in the mountains, but then you have a deficit of mass in this low density root. That's the idea. So we can do this sort of gravity modeling in space very easily because of the way we communicate with satellites. When a satellite is moving away from Earth, you have a Doppler shift in the signal. Does everyone know what a Doppler shift is? So you experience a Doppler shift when an ambulance drives by and you hear the sound go and the pitch drops. So what's happening is, as it's moving away from Earth, the signal wavelength is effectively getting stretched out, and as you move towards Earth, it's getting compressed. So by looking at the slight change in the radio frequency being sent to and from Earth, you can reconstruct the velocities of the spacecraft. If you know the velocities, then you can determine acceleration. And in space, where there are very few forces acting on the spacecraft, most of the accelerations, after you account for radiation pressure from the sun, comes from changes in the strength of gravity. Very slight, but enough that you can measure them. So it's useful to describe some of the kinds of gravity anomalies you would expect for different kinds of internal structures. This is a case of area isostasy, a theory that was developed after the time of Pratt. And essentially you have a mass excess, like we talked about, in a plateau of the crust. And you have an essentially equal and opposite mass deficit in the root of the plateau. So what happens if you're a spacecraft flying over this? You feel the extra gravity pull from the excess mass of the mountain, but at the same time there's a deficit of gravity pull from the low density root. But you are a little bit closer to the mountain than you are to the root, and so when you combine them, they mostly cancel out, but you feel a little bit of a positive gravity anomaly. So this is the area isostasy is analogous to this iceberg that I described earlier. If the compensating mass is deeper in the mantle, then you still have the equal and opposite mass deficit. But in this case, your satellite is much closer to the mountain than it is to the mass deficit. And so what you're left with is a larger gravity anomaly in some. And the principle here is that the deeper you have this mass deficit that's holding up the topography, the larger the gravity anomaly relative to the size of the topography. So really what's happening here is there's mantle flow that's pushing up on the a flow pattern that's resulting in this topography. And I'll talk about how I model that in a couple slides. There's one other scenario that would be good to try to understand, and this is the scenario where you have a low viscosity asthenosphere, like we have on Earth. So if that's the case, then you could have huge density anomalies in the lower mantle that are all sorts of stuff, but they're not mechanically coupled to the surface. And as a result, you can have large gravity anomalies that are not correlated at all with surface topography. And we see that on Earth quite a bit. A lot of the geoid anomalies on Earth aren't correlated with continents or other high topography. So the data we got back from Venus is from the Magellan mission, and that collected data in the early 1990s. And one of the first observations that was made is that you see topography on the top and the geoid on the bottom. The geoid is a gravitational equipotential surface. So a high geoid basically means the same thing as high gravity. So one of the things that you'll see is that there's a really strong correlation between the topography and the geoid. And so that rules out a scenario like this, which we have on Earth. And so one of the early conclusions of this mission was that Venus doesn't have quite the ultra-low viscosity layer in the asthenosphere that Earth does. So there's one difference between Venus and Earth. So this plot is basically sampling the gravity and the topography at every point on these two plots that I showed here. So you take one point, one geographic latitude and longitude, take the topography and the geoid, and plot them as a point on this scatter plot, and do that for the whole globe. And so when you do that, you end up with some, you can see some trends in the gravity and topography. And this slope here corresponds to the trend that you would expect if topography is compensated by crustal roots. So you do see quite a bit of these trends. You can sort of visually pick them out, that trend with this 3 meters per kilometer line. But a lot of the planet is trending along a much steeper line. Remember, we were saying that the greater the compensation depth, the larger the amplitude of the geoid relative to topography, and steeper the slope. So there are at least 2 different depths of compensation going on. On Venus, you have groups of crusts that are holding at plateaus, but then you also have really deep-seated mass anomalies that are pushing up on topography. In order to model this, I do calculations of viscous flow, and this is the only equation. This is the only slide I have with equations, but it's worth explaining what these are in principle. The top one says that the divergence of the velocity field equals 0. And this means if you were to take a box of the inside of the planet, the amount of flux going into that box has to equal the amount of flux going out. So you can't cause any compressible flow. The second equation is a variation of the Navier-Stokes equation. Believe it or not, this is a simpler version of the old Navier-Stokes equation, but it deals with the pressure distribution, the body forces, which come from gravity and mass, and then the middle term is related to the viscosity, degrees of viscosity. So it's an application of Newton's second law to viscous flow, essentially. And then speaking of gravity forces, the bottom equation deals with the gravity field that results from a distribution of mass. And modeling how different mass anomalies interact with each other in self-gravity is actually a big part of this calculation. But what results from this when I apply lower boundary conditions and upper boundary conditions is I can generate velocity flow fields inside the planet. So you might have something that looks like this under a volcanic rise on Venus. You have flow of the mantle that goes up and diverges.
Okay, so the result is that that I can make a map of the thickness of the crust on Venus, which is shown on the top, and then a map of the mantle flow patterns. And the red essentially mean the areas where there's upward flow, like I showed in the previous plot. Anywhere where there's flow upward, it's red. If there's flow downward, it shows up as blue. And so you see a lot of these red spots that are upwellings in the mantle, where you have really buoyant mantle. And mantle can be buoyant if it's a hot plume or if it's chemically less dense. But you see in the crustal thickness plot, a lot of the continents that we saw earlier have thick crust, but then some of the other continents are really supported by this deep mantle flow. And there are at least two different genres of continents on Venus. There are crustal rises that have thick crust, and then volcanic rises that are compensated more deeply. And then there's Tharsis Terra, which might be different from either of those. It's sort of a one-off feature that no one understands yet. This is a visualization made by a Canadian geophysicist showing what it would look like if you were sort of swimming in the mantle and looking up at the underside of the crust for the crustal thickness map I made. And essentially you can see how the continents have what look like, they have deep roots that look like keels of a ship. And these are part of what's supporting the weight of all the topography. So just to briefly touch on what this means for the formation of the continents, here I have plotted out in a paper I did a few years ago the crustal mass that's accumulated versus the integrated mass deficit in the mantle. And for just about all of the continents, everywhere where you've accumulated thicker crust, you also have a mass deficit in the mantle. For this one in particular, it's interesting because this is a continent called Thetis Regio. The central really high plateau of the topography is, it corresponds to very thick crust. But then there's a broader swell in topography that really is caused by this broad upwelling in the mantle that's pushing up on the whole region. So it's a combination of these two effects that make the continent we see. And this is more consistent with the upwelling hypothesis that we saw earlier. Another thing I want to mention about Venus is some work that I've done with colleagues from NC State and Imperial College London about a new style of tectonics on Venus. So I have colleagues that are photogeologists. I can't claim credit for any of this part of the work. This comes from people who stare at grainy radar images all day and figure things out from them. But you look at some of these structures and you can determine that there's been a sense of shear. So these are some sort of transpressive structures that in many cases outline blocks that are relatively undeformed. And so the thought is that there's some sort of block deformation that is analogous to a jostling ice pack, where you have chunks of ice that move past each other but stay relatively undeformed inside. On Earth, this is analogous to some of the kinds of block motions we see in the Tibetan Plateau and the Tarim Basin. So this is a new kind of tectonic activity that my colleagues are working on characterizing in a paper we're hoping to submit soon. But if you have tectonic motion, you really need some sort of forces driving it. And we know what those forces would be for Earth. So in a plate tectonic system, you have forces from the gravitational potential energy of a mid-ocean ridge, where the ridge is thermally buoyant, and so the ridge itself tends to be higher up above the ocean floor. And as a result, there will be gravitational forces that want to push away from the ridge, and this creates a force that contributes to plate tectonics. There are also forces from convection in the asthenosphere that exert tractions on the base of the lithosphere. but most of the forces come from subduction. So a subducting slab is very dense, it's cold and dense, and as a result, once it starts to subduct, it will pull everything behind it and drive this downward convection. As it goes downward, often there's a rollback of the hinge, and the suction created by that tends to pull continents along with it. Even when a portion of the slab breaks off, you can have a flow field induced that tends to entrain the rest of the lithosphere behind it, even if it's not mechanically coupled anymore. So we know all of these forces are involved with plate tectonics, but on Venus, what would the analogous forces be? We don't have any of these things that were described. You have some stresses from volcanic loading, but those don't act on these broad scales that on which we see these structures. But one possibility is attractions from the mantle flow that we were talking about. So as the mantle flows, it exerts what I call attraction on the bottom of the lithosphere. So it's really pulling at the base of the lithosphere. And one of the things I can do from the model I showed earlier is map out all the places where you expect there to be the kinds of compressive stresses that would produce transpression that we saw earlier. So this is a map of the sigma 3 component of the stress tensor. So it's the most compressive principal stress. And everywhere that has some amount of blue, you would expect there to be the right kinds of stress conditions for these structures. And what we see isn't perfect, but there is a statistically significant correlation of the orange structures over the blue regions. And so this indicates that the mantle convection stresses are at least contributing to this style of tectonics we see. And while we have plate tectonic forces on Earth, it's these really strong mantle tractions that are probably driving tectonic motion on Venus. One of the interesting implications for this that I presented at the Lunar and Planetary Science Conference this year is that you might expect there to be Venus quakes. So a Venus quake is like an earthquake, but on Venus. We have different names for earthquakes on all the planets, moonquakes, Mars quakes. On Venus, there might be a significant amount of seismicity. And so on the moon and Mars, we do have quakes, but most of the tectonic activity happened early in its history. If you have mass unloading that happened early on the moon, or a volcanic edifice that was placed on top of a plate on Mars, you tend to get a lot of breaking of the lithosphere to relieve the stresses associated with that. But then once everything is below the yield strength of the lithosphere, it stops. It might have a tail off, but there's not going to be much seismic activity after that. On Venus, if the earthquakes are caused by this mantle flow, then you would get an Venus quake that relieves the stress. But then over time, the mantle keeps flowing, builds up stress again, and then it breaks again. And so we wouldn't expect there to be much less seismicity today on Venus than there was a long time ago. And that's really helpful for studying the interior of Venus. Most of what we know about Earth isn't from gravity, like I was describing. It's from seismology. We have tomography data, we have reflection data, and this allows us to really image what's underground. And we study gravity for planetary contexts because that is the kind of data that's easy to collect. It's a lot harder to actually put something on the ground and measure earthquakes. But if we could do it, then that would tell us a whole lot about the inside of a planet. And there are a couple of different ideas on how you would do this. There's a traditional seismometer that you could put on the surface, it just wouldn't last very long, as the Soviets learned. You could send a balloon into the atmosphere, and it could listen for the really long period pressure waves that come from transmitting seismic energy into the atmosphere, which would be significant on an atmosphere as thick as Venus's. And then you could, from orbit, also look at waves in the top of the atmosphere. So there is an air glow that occurs in the ionosphere from waves that should, in theory, be detectable from orbit. So there are a bunch of different ways that we could go to Venus. And when I go around giving a talk like this, I'm trying to extol the virtues of Venus and explain why it would be so interesting to study Venus, in part because you never know if someone in the room is going to be on a review panel for the next round of NASA missions. And yeah, Venus is a really interesting planet to study, and there's some really interesting stuff that we could do to get at these fundamental questions of why Venus is different from Earth. So I have one more slide, but before I finish up, I wanted to make a quick plug that we have over the next few years, we have openings for PhD students, both in geophysics and in planetary science at Baylor. We're in a nice new $100 million facility, and there are lots of projects that I'm really eager to start working on with PhD students. I'm working on a grant right now with colleagues from Goddard Space Flight Center to study the gravity data from the very end of the Messenger mission, the first spacecraft to orbit Mercury, in order to study the properties of the crust. I would love for someone to be interested in Mars. I have not done any research on Mars, but there's a seismometer on its way to Mars that will land the Monday after Thanksgiving if everything goes well. For Mercury, I forgot to mention, in about 4 hours, there's going to be a rocket launch to Mercury, the second spacecraft ever to orbit Mercury. The European Space Agency is sending one there. But yeah, Mercury or Mars neither of them are quite as interesting as Venus, but they both have data, so they have that going for them. So it would be really interesting to use some of this data from the InSight lander, which will collect seismology data, heat flow data. And we also do near-surface geophysics work. I have a graduate student right now who's studying terrestrial impact craters, because that's a process that's so important to airless bodies in the solar system, like the moon. But on Earth, we can actually go to the craters and study how they form. So I'll finish there. Thanks again for the invitation.